Okay, I'm recording, so don't say anything awkward. I have to keep myself to that too then. All right, let's take a look at the summary sheet. You guys can get it on Google Classroom if you'd like. I think I made it public. Let me just check on that real quick. But while I do that, let me just discuss what you see here, okay? So first thing on the top is the statement that you'll see at the top of the exam. Obviously, I know there are many ways for you to get around this. I'm just trying to encourage you to be honest. So here's the info. It says the exam consists of 20 problems. You must complete it in 80 minutes. All answers must be submitted on exam login. You also must submit evidence of written work using Google Classroom or email. Detailed work does not need to be shown for every problem, but please provide sufficient proof that you engaged with the problem and did not receive an answer from another person. You're permitted to use online and print resources, but you may neither give assistance to nor receive assistance from another person, both during and after the exam time. If you answer no to the question below, please submit the exam and do not continue. The question is just going to say, do you agree to abide by these regulations while taking this exam? Okay, so if you say no, submit it, get the F, and move on with your life. There you go. All right. Any questions on the format of the exam? It is Thursday. Yes, it is next class, Thursday. Let me make sure that you all have access to it online. Okay, Zoom friends, it is now accessible to you online. It's up at the top. I'm recording, yeah. It says Linear Algebra Semester Review, and it's under General Info. Okay. Any questions on the format of the exam?
Do you think it's going to take a full 80 minutes?
Yeah, probably. Okay. All right. Couple more comments about format. Thank you. It is not all multiple choice. There's a lot of questions that will say like, do this work and then report such and such as your answer. Okay. So be aware of those and think carefully. Of course, if you goof up the very last step of entering your answer, but I can see work that leads to the right place, I will give you credit for that problem. Okay, but it's much easier to grade if you can just get it right in the first place from the thing. Okay. Of course, I'm not going to read all these bullet points, but I've tried to organize it by chapter. And I will tell you this, it's what you see on this is comprehensive. In other words, there's nothing that you need to study that's not on here. But of course, I can't test you on everything on here. Okay. With only 20 questions, I can't cover everything. So if you get to the exam and you're like, the invertible matrix theorem was nowhere. Sorry. Oh, it's a pretty important one. So yeah. So, and I think I've covered it well. I revised it from previous years and made sure it fits what we actually did. But if you find something wrong, let me know. Benji. Oh yeah, of course. It's open, just like the whole year. Calculators allowed. You know, use your online resources, use your notes. Just don't speak to each other or communicate with each other in any way. Yeah, it's the same test. Yeah.
Do we need to rep and matrix multiply by hand?
No.
When it's not like
No.
letters?
No. Okay. Any other like format questions or just general questions? Okay. All right. Next thing I want to do then. So this is what I have planned for today. I got two main things to review. I want to do problems from my friend's midterm review. And that's what I gave you all on paper. And you guys online have a link there to it. And I believe in class we did 1 through 3 last time. Did we do 3? Oh, but the class before.
One of them.
Okay.
Like 2 classes ago.
All right. And then I also, this is way more than we'll ever do, but a couple of years ago, I Googled sample linear algebra exams, and there is this wonderful website that I found from Bates University, where they just have this compendium, it's beautiful, of all these past exams. And so I just Googled compendium, yeah. So I just printed a few, and this is a wealth of good problems. So I'm going to pull some from this for us to do, and then you are welcome to explore these too. So they're all great problems. And look, they use the same book as we do. Lay, right? That's the book that we use. Okay. So I've actually taken past questions from those exams, but you'd have to comb through all of them to find it. Oh, yeah, sure. Let's see.
All the ones that took you.
Yeah, exactly. Sample exams. I think a lot of them have solutions posted too, but it's just fun to see like which ones you can do and stuff. All right, so let's start with my friend's test, and that's this one. Okay. So I just kind of want to do a mix of me doing stuff with you and you doing stuff on your own, and then we compare our work. Yeah. No, this is a part of a special program where someone gets a master's in math education, and they have to go back and cover stuff that they previously did in an undergrad. It is way too easy for a 600 level class. Yeah. Okay, let's tackle 3 together. Ready? So it says solve the following homogeneous linear system and decide whether it has a non-trivial solution. How would I ask this? I'd probably just ask it as true or false. This has a non-trivial solution. And since there are 4 equations and 4 unknowns, you can't tell just by looking at it. So we are going to have to ref. So let's go through the process and we'll see where it takes us. I'm willing to do the typing if you want to just sit and watch, but if you want to check me on the calculator, that's fine too. This is the slowest program ever. What am I doing? Am I doing anything fun? No. Is that this weekend?
Yeah.
Oh, so you all will be gone on Monday?
Yeah.
Is Monday a gold day?
Yeah.
Oh,
Yeah.
that's sad. Well, be safe, okay? Don't get in trouble.
Okay, well,
Yeah, right.
Maybe I will Zoom with the class. Maybe we'll say hi. I can't say I'll stay.
Yeah, you can just make sure that you are, in a good state of mind.
Oh, I'll be in a.
thank you.
A school appropriate state of mind.
Oh, appropriate.
Thank you. I think, I guess that's when,
Well, I mean, like.
I don't know. We're not allowed to sanction that, but
You're definitely allowed.
No, I know sometimes it says you're not allowed to practice.
okay, let's go around the room. Eric Sander, look at the screen. Does this have a pivot in every column? No, right? So here we see, you can't see, so this guy is free and this guy is free. This is the augmented, right? So there is a non-trivial solution. Your main takeaway here is that needs to be that free variables indicate there's more than one solution, right? So that's the answer. Could we write it out specifically in parametric vector form? Sure. We're not going to do that. We've done it so many times. Unless you want me to. You want me to write it out?
That's just the x1.
X1 equals, X2 equals, and then splitting it up into vectors. Yeah. Okay. Good to go on that one? All right, now, this next one, I'm going to leave you to think about for a little bit because this is a great problem. And I put one, I'm just going to level with you. I put one like this on the exam. Okay, so put a big star by number 4. Okay, it says write the matrix A as a product of elementary matrices. I love this problem because it gets at some really good ideas. So here's the deal. Remember, you use elementary matrices to ref a matrix, right? It does the steps of a ref. Are these 2 columns linearly independent? Yes, they are not scalar multiples. Therefore, this thing is invertible. We know that by the invertible matrix theorem, and therefore it's row equivalent to the identity. Okay, so spend some time. I don't think anyone's going to get this immediately. All right, spend some time to figure out how can A be written as a product of elementary matrices. Take it away.
It could be more than 2.
Yes, it will be more than 2 matrices. Okay, here's the hint. There's an elementary matrix you can apply to A. Oh, sorry. There we go, and there we go. Okay, there's an elementary matrix you can apply to A, and then another one, and then another one to produce the identity. So the matrix A is 3 elementary row operations away from the identity. This means if that's true, your job is to find these. Determine the first one, the second one, and the third one that will do that. And then elementary matrices are invertible, which means that E3 inverse times E3 times E2 times E1 times A equals E3 inverse. Then those go away. Then stick an E2 inverse in front of there, right? E2 inverse, E2, E1A equals E2 inverse, E3 inverse. And then do another one. Now, Carson's method was a little more intuitive than what I'm showing here, but then the last one is going to show that A can be written as the product of these 3 elementary matrices, right? The inverse of the first operation you do, the inverse of the second operation you do, and the inverse of the third operation you do. See if you can do it now.
How did you know that there would be 3 elementary?
Because I just did it.
Because if you rough by hand, it takes 3 steps to get to the identity.
Oh, okay.
If you rough by hand, it takes 2 steps. Got it? Okay. You have the sheet. If you want to go on, you can. If you want to wait, that's fine.
You can use the power of -1 too.
You can, but there's a more intuitive way to do that. Because if this is an elementary matrix, watch, this is its inverse. Take away the negative and you got your inverse. So, Mr. Cook, I got it. So, let me do this. The way I did it was I ref by hand, and I basically do each one I had. So I started again. So the previous state I was in, the bottom row was the inverse. And so I just kind of taking it like multiplying one matrix at a time. So I started with that first bottom row, and I added 3 layers of the second row, the second row to the first. Yeah. And then I did it. So you just do after that first process. So,
Yeah. So I did get the answer, but what were you talking about when you did like erase the negatives? Because I have all the.
Sure. So you wrote the matrices out as they are. Here, let me just show some more stuff here. Okay. All right. So here's all my work. Online people, you can see this. Okay. So I started with this, and then I just refed it. So I did 2 times row 1 plus row 2 and wrote my answer. So we're here, getting somewhere. I changed the sign of the second row, so I just negated row 2 to get, ignore this, don't pay attention to that, to get this. And then I did 3 times row 2 plus row 1, and now we're at the identity. So Carson's approach was to just say, do the opposite of this, and do the opposite of this, and do the opposite of this, and that'll get you back to A, right?
Yeah.
Mine was a little more like writing out the matrices, but that's okay. His method's probably a little more intuitive anyway. So I wrote down right here is the first matrix, which we do to A. What is it? We take 2 times row 1 and add it to row 2. See, it's an elementary matrix which does that work. It leaves row 1 alone, and it does double the first row and add it to the second one. Are we clear on this?
Yeah.
People feel okay about that? Right? An elementary matrix does 1 elementary row operation, and it does the operation that was used to perform it. So I said that backwards. It is made using the same elementary row operation that was done on the identity. So you just have to track with what you're doing matrix multiplication here. 2 times the first row plus the second row, that's what that'll do, right? It'll leave the first row alone by putting a scalar weight of 1 on it and 0 on the second row. And this will put a scalar weight of 2 on the first row and 1 on the second row.
Oh.
Okay. Then I negated row 2, so that's what this elementary matrix does. And then I did 3 times the second row plus the first row. Yeah. Okay, so these matrices now need to each be inverted to find A. So what's the inverse of this matrix? Just make the 2 negative. If you take 2 times a row and add it to another row, the way to undo that is to take -2 times, or what did I say? -2 should be +2 then, right? How do we do the inverse of negating a row? We negate it again. So that's why that one works. And how do we do the inverse of taking 3 times a row and adding it to another row? We take -3 times that and add to another row. So that product gets you A. Now we've shown that A is a product of elementary matrices. So I just really thought the problem was interesting because it really combines this idea of inverses in elementary matrices, and it relates to the invertible matrix theorem, because that's the whole reason this can be written to the identity. So there is one out of the 19 actually. The first question is, do you agree to abide by these rules? So 1 out of the 19 is that problem.
Wait, so Mr. Cope, when we're doing this, I understand where you got the matrices for the left there.
Yeah.
But why would they not be the opposite initially? Because wait, hang on, I'm looking at my own. Like, why would you not use those matrices as like elementary row operations you would use to get back to I? Because like when I bereft it, right, I then went from starting with I.
Yeah.
I moved left, right? So like I used the same row operation that you did.
Yeah.
And then I moved backwards. So like my first one was 1 times or 1 0 0 -1.
Yeah.
But why would it not be why would that not be the inverted matrix that you're using? I feel like I'm saying that wrong.
I'm not sure exactly what you're asking.
No, I'm not.
Did you try to start with the identity
Yes.
and build A?
Yes.
Okay, I was thinking of trying to do that too, but I just don't know how to do it.
So
Because
like, let's just get some.
this would mean that, okay, if you do this, that's gonna leave the first row alone, and it's gonna take 2 times here and add, right? So it's gonna be
Yeah.
this. Is that the result of that?
Should be, it's just identity times that, so yeah.
Good, yeah, that's the result. But now what do we do next from this? You know,
Would you just do what your next step was in the opposite direction?
oh, we could. So you mean we could just negate this row, you mean?
Yeah, it's really hard to see doing that.
Yeah, because then you have
Because
to.
I tried to do this too, and I got to this stage and I was kind of like, okay, I don't really know where to go.
Because
You triple.
because the issue with, okay, the thing about that's good about refing when you get the stepping down nature is that you don't mess with the other things when there's zeros there, right?
Yeah.
That this process is gonna mess with this element, and it's hard to see then where that's gonna go.
So yeah, I did a ref, but then how would I shake those different matrices that I used, or those steps that I used from a refing and make them into matrices that will apply to A?
Okay, right here. This is that, the answer is right here. If there are 3 matrices that you apply on the left to get I, those same 3 matrices, but inverted, will get you A. And that's the reasoning that I walked through here. Look, if you've got this statement, invert E3 over here, they go away. Now we have 1 copy. Now invert A2 over here. Now we have our copy of E2 there. And then do it with E1 over here. So you get E1 inverse, E2 inverse, E3 inverse.
Okay, that makes sense.
Okay. Want to try another one?
Yeah.
Yeah, actually.
Yeah. Or do we not, or just to use our time well? Like I don't want to.
No, I think this is a good one to try.
Or are we gonna move like,
I would
otherwise
like
then
to
move
do
on to the next problem?
Yeah, I would move on to the next after this.
I don't know, I just feel like this is definitely a problem on the test.
You want to see it again? Okay, let's do it again then. All right. So remember now, all I have to do is start with an invertible matrix. That's the only requirement for creating my problem. Okay, so here's A.
So we're doing the same time process.
Same type of problem. Ready? And if you are bored with this, go on to anything else. You've got the page there. You can try other stuff. Okay, so here's the matrix A. I'll try and make it a smidge more challenging. 2, -3, 1, 5. Okay, I'm going to pause the recording and freeze the screens, and then we'll compare our work in a few minutes. We'll start the recording again. I double checked my work with the calculator, but it'd be healthy to just explain it too.
Should I look at my notebook?
Yep.
I'm not very good. Yeah, almost right. These are 2.
You did it with 5 matrices.
That's an idea.
So you doubled you started by what? Doubling the first row?
No, 2 half. This is the inverse of my first. So like I made, my first move was to divide by 2, right? But made that E1, and after that I took the inverse of all these. The E1 inverse, E2 inverse, E3 inverse. E4 inverse.
Just sit down and study it. I can't like look at it.
But like, is that the right process?
Yeah.
So like find, like this going from divided by 2, this would be divided by 2, and then take the inverse of that. Then, okay,
That would be 2.
okay.
Yep.
Okay, I'm not sure.
Okay, so step 1 for me, I wanted a 1 in the top spot, so I switched the 2 rows. So what is that? That's really this matrix. That elementary matrix. Step 2, I wanted to go from here to here by doing -2 times row 1 plus row 2. So that matrix is right here. Leave the first row alone, -2 times row 1 plus row 2. Okay, then I go from here to here by getting a 1 right there. So I multiply the second row by -1/13. That's that matrix. And then I take -5 times row 2 and add it to row 1. So that's changing the first row. That's why it appears there. Now, I kind of foolishly went to my calculator and was like, oh, I'm just going to multiply these and check if it was right. And I got this ugly looking matrix. Like, what did I do wrong? Well, I forgot to invert all these things, right? Now, surprisingly enough, guess what matrix appeared when I did this?
Transpose that.
Thought this would be such a great question. I wish I had thought to ask it on the exam. So suppose a student was doing this and they incorrectly went to their calculator to check, and they multiplied all this and they got this weird looking matrix. What is that weird looking matrix? The term. Add to it. The inverse of A. Beautiful, right? Because why? Wait.
Because you didn't work that. So
Yeah. This whole package of things, when multiplied by A, gives us the identity. That is the very definition of an inverse, right? This whole thing, when multiplied by A, gets us the identity. So this whole thing is the inverse. Remember, that goes back to the logic of, remember, the steps that take A to the identity, take the identity to A inverse. Okay, so what do I have to do? I've got to invert all these, which I did over here. The inverse of the first thing is just itself. Change the -2 to positive, change the -1/13 to -13, and change the -5 to 5. Okay?
but Mr. Coates, when you multiply, it starts from the right-hand side and it goes to the left.
Yes, yeah. Or you don't really have to think of it that way. You could think of it as going like this product gets multiplied, it's associated, you know? Do that first if you want, then stick this on the left, then stick that on the left. If you were doing it by hand, you would think of it as right, you know, left to right.
Yeah.
Okay. All right, let's put that problem to bed. We've done enough of that, okay? It's only 1/19 of the exam.
Do you like break?
Yeah, what do you want to see? Like this stuff here? Good.
Okay, I did it like 6.
6, did it work?
You got there
It
eventually.
worked, it worked. It's good.
Wait, so is like the first question, is it kind of points?
Does it count as points? What do you mean?
You know, there's 20 problems.
Yeah. You get 1 point for answering yes. I will abide by these rules.
I figured out what it is wrong.
Oh, good.
I just added.
Okay, at least a 5%.
Or
Okay.
it's
Yeah, you'll get a 5%. Okay, question 5. And then you might want to break. I don't know. I kind of don't want to take a break today because it's such useful time, you know, to do these problems together, but up to you. All right, here's question 5. Write the vector 2, 3 in R2 as a linear combination of 1, -1 and 3, 4. Do V1 and V2 span R2? Okay, let's just start. I'm just going to ask a random person a question. Let's focus on this. Any volunteers? Focus on that last question. Do they span R2?
If they're linear combinations of each other, then they wouldn't span R2. So we should see the linear combination of which they are.
Good job. We can tell easily, can't we? They're not multiples of each other, so they do span all of R2. We got that question out of the way, right? Okay, now, write this vector as a linear combination of those two. We know there's got to be a way, so we're going to ref, right? So let's set it up. Yes. In fact, let me write it first this way. Oh, shoot, I want to stay on the same page. Hang on. All right. Let's say that we want to find a constant to put in front of the vector 1, -1, and a constant to put in front of the vector 3, 4 to arrive at the vector 2, 3. Okay, so of course the answer is augment and ref. Has anyone done it yet? Thanks. So there's our answer. Those are the scalars that we can, 5 7s. Those are the scalars that we can put on those vectors to arrive at 2, 3. That's a classic question. Very, very important idea. The concept of, can you write a vector as a linear combination of others? You could think of these as the beta coordinates of those basis vectors, right? Those are the beta coordinates. Those are the weights you put on those vectors to achieve 2, 3.
Wait, since it says write the vector B as a linear combination, just plug -1 7.
Yeah. You would literally just say this belongs here and this belongs here. Good? Okay. Go on.
Yeah.
Okay. All right. Maria, I'm going to have you take a stab at 6. Decide whether the vectors given there of R3 are linearly dependent or linearly independent. If dependent, exhibit a linear dependence relation. Just tell me what to do. You don't have to actually do it. Okay, let's do it. Okay, so set up a matrix with the vectors in the columns, she says. So 1, 1, 2, 1, 2, 1, and 1, 3, 0. Did I get that right?
Yeah.
1, 1, 1, 1, 2, 3. Okay, good. All right, someone not Maria, tell me the conclusion.
There's a free variable.
There's a free variable, so dependent. So number 5 on the exam, no, number 6 on the exam would be that this set is linearly dependent. Hey, at least you can feel confident that you won't ever have to explain any of your answers since it's all on.
Oh, it's on the exam login.
Yeah, it's on exam login. Singbum, say it again. How do we know? There's a free variable, right? Not all of the columns are pivot. Okay, so lack of a pivot. You know what I should do? I should offer, I don't know, wait, I could enforce it. It would be fun to offer extra credit if you would take the exam without notes. You know, I don't know, right? I don't know. Might not be worth it. Right.
I feel like most
Yeah.
But you have to memorize all the translations, like all the translation matrices.
Oh, those, yeah. Yeah, there's only one question that deals with that. And can you predict the question? No, predict what the question's gonna say. Come on, you do it.
If you reflect over a line that's a line not on the origin.
Project this matrix.
Good guess.
Find the sum of the coordinates that would reflect this point over, that you would end up with.
There you go. There you go. Nice.
Some abstract.
No, I'll actually tell you how I did it. I won't tell you what kind it is, but it's very similar to that. But the question is, report as your answer the lowest of the 6 coordinates. Okay, so
As in like
the lowest number.
6 coordinates.
Well, 6 being the x, the y, the x, the y, the x. It's a triangle. Yeah. Okay, there you just got another big hint. Okay, so what he said, what Cody said, is very good to be. Remember, it's going to be one of those classic: move to the origin, do the operation, move off the origin. You know, we could cover one of those. Okay, so wait, we didn't finish this problem because it said exhibit a linear dependence relation. So check this out. If we write this in parametric vector form, because remember, there's really, let me check if I'm recording. What's wrong? Oh, sure, thank you. Okay, remember there's really a column of zeros there on the end.
Yeah.
Okay, so that's why x1 is -3x3, because what we're trying to solve is we're trying to say, are there non-trivial solutions to ax equals 0? So now we know that there is a non-trivial solution. We know that -3, 1, 1 is a solution, but that's not a linear dependence relation. That's a solution. That means that A times that vector equals the 0 vector, which means that a linear dependence relation would say -3 times A1 plus A2 plus A3 equals 0. That's a linear dependence relation. It's a statement that tells us how the columns are related. Okay, questions? Zoom people, questions? Keeping up okay? All right, 7 is a dumb question. We're not gonna do it. It says solve the following by backward substitution. Nah, we would just for ref it. No, it's dumb. 8, 9, and 10 are really cool though. So let's do all of those. I'm gonna give you guys a chance to think about 8 before I just spill the answer, okay? So read it. Let me go back to the page so that you can see it on the screen. Pause for online, pause for in-person, and pause the record. 423.
Yes, I got it.
Nice, cool. Okay, let me explain 2 ways. Well, he can explain his way because that's smart to think of it. Okay, here's what we know. T of 1, 2 is 5, 6. T of 2, 1 is 4, -3. Okay, we're supposed to find T of -2, 3. We need to use the fact that this is linear. Here's the deal. This is the special fact about linear transformations. T of C1, V1 plus C2, V2. In other words, the transformation of a linear combination is C1 T of V1 plus C2 T of V2. See, I did the problem without ever finding the matrix that does the transformation. And I think that's what the author probably intended here. Because what do we do then is we say, all right, let's take this input vector and write it as a linear combination of the 2 given vectors. I'm going to call them V1 and V2. Okay, so when I did that, you know, I just did that by rereffing.
How do you know that negative, so you're saying that -2, 3 is a linear combination of V1 and V2 just solely because it happens to be.
Because I want to write it as C1 V1 plus C2 V2. Yeah. Okay, so here are the scalars that I found, but there was my mistake. Those scalars were actually wrong. Those scalars, in fact, should have been 8/3 and -7/3. So this should be, let's fix it. This should be 8/3, and this should be -7/3. Okay. So then I said, well, if we're trying to transform -2, 3, we're really transforming this linear combination, which means I can take 8/3 times the transformed version of V1 minus 7/3. Let me fix those numbers. What is it? Minus 7/3.
Where did you get 8/3 and -7?
That's from rereffing to find the scalars that go in front of V1 and V2. I'll show you. Right here. Right there. I'm finding what scalars do I put on 1, 2, and 2, 1 to get -2, 3. Okay. And then here's the answer. I just took 8/3 times the first output vector minus 7/3 times the second output vector, and that's how we get 423.
Wait, where did you get 5, 6? 5, 6 came from multiplying
5, 6, what?
5, 6. That vector.
Oh, that's the other method. Hang on. Cut this off. This is my method, and then Cody can talk through his in a second. Or other people did it too. All right, so then this gives us the 423 that we wanted. Okay, now talk through what you did, Cody. Okay.
So like, if you're with the numbers, so if I type it like,
Want to erase all my stuff?
sure.
There's a eraser right here.
I just treat it like an equation, like an A
Mm-hmm.
times X equals whatever. But it said like, if my kind of the matrix that we want to use to transform it is A, then the B would be like the matrix with the 2 vectors in it.
Call it X instead, because that's how we usually do it, right? AX equals B.
So it was a matrix, that's why I called it that.
Oh, okay, fine. I gotcha. Yeah.
This is matrix B, right, with the 2 vectors in it. That equals B prime, that's what I called it. Then just multiply that by the inverse on both sides. And then you just get A
Wait,
equals.
why can you do that? Don't you have to multiply the inverse on the left side?
No, as long as you do it the same way on both sides, it's fine.
It's like dividing.
Good job.
Oh, I
If like
didn't
you
know.
can't do it on the left and on the right, you need to do it both on the right or both on the left.
And B prime is made up of the solutions.
Yeah.
Yeah.
And then now that I have this, then I just take A and multiply it by X, which we got, and that gives us B.
Mhm,
That's like 423.
mhm.
Ah.
That's really nice. That's a much better way to do it. Here, see, look what well, let me describe his method a little differently. He took this unknown transformation matrix and said, pretend that those things are missing. It transforms 1, 2 into 5, 6, doesn't it? We have that. And it transforms 2, 1 into 4, -3. So he just said, what is this mystery matrix that will do those things? And then this is the process that he went through to find that mystery matrix. And then he took the input vector, what was it? Whatever.
-2, 3.
Yeah, he took -2, 3 and applied it, -2, 3, and got 423. Yeah. Now listen. That problem like that's not on the final, but why did I give it to you? Because I want you to remember that linear transformations have two very important properties, okay? Let's go over that because that concept is on the final. When something is called a linear transformation, that statement that I wrote up above basically summarizes it, this whole T of C1 V1 plus C2 V2, that whole thing. But our way of seeing it before was this: T of U plus V equals T of U plus T of V. And T of CU equals C times T of U. This professor wrote like 2 good questions that tackled those. 8 is really good because it tests the student's knowledge of linear transformations. And 9 does the same thing. Now, I'm not going to do 9 with you because it gets into a lot of arithmetic. We'll skip 9. But look at what they're saying. It says, hey, there's a transformation which takes x, y, and turns it into x plus y, x minus y, and x. And what the professor wanted them to do was to test those 2 rules using that transformation. What I do want to show, so A ends up working. It's actually harder to show something works than that it doesn't work. Okay, so let me show you 9b. This one's kind of interesting.
There's a square in it, but make it complicated.
Yes, exactly. So let's look at y, right? Okay, so here's the deal. T of xy equals x and x plus y squared. So I want to show you how this violates the sum rule. Let's take 2 vectors as inputs and try it, okay? Let's take vector 1 as 1, 2, and vector 2 as 3, -1. Okay, so I'm going to find T of 1, 2. T of 1, 2 would just be 1, 5. Right? And T of 3, -1 is equal to 3, 4, right? You following me or no? It's the x coordinate and then the x coordinate plus the y coordinate squared. So we need to test, is the sum of the outputs the same as the output of the sums? Let's try that. Well, what is the sum of the 2 inputs I've tried? Let's try 4, 1, right? So this means if we sum the 2 inputs and then transform it, this thing gives us 4, 5. But if instead we just do the 2 outputs and add them, so let's take output 1 plus output 2, that gives us 4, 9. Do you see how it fails? The fact that these 2 do not equal, this means that T is not linear, because we've shown that it violates T of U plus V equals T of U plus T of V, right? We've taken a counterexample and shown how it fails. 1, 2, and 3, -1. When they get transformed, we get these 2 vectors. If we add those 2 outputs, we get 4, 9. But if instead we add the inputs first and then transform it, we get 4, 5. So we've shown that it violates that rule. What do you think? Get that okay? When I transform the sum of the inputs, which is happening right there, see how this is the sum of the inputs? 4 and 1, we get something. And that's different from when I add the 2 transformed vectors, right? I add the transformed vector of 1, 2, and the transformed vector of 3, -1. When I add those, I end up with that thing, 4, 9.
So that isn't a linear.
It's not a linear transformation, right? To show that something was a linear transformation, that's why I'm skipping that part. We would have to show that this thing works for every vector in the space, and this thing works for every vector in the space. This one's easier because I can show it fails with one counterexample.
So then how do you show something?
You'd have to prove it for both. That's not on the quiz, because that would be a long proof. Quiz by quiz, I mean final exam.
And then for the TCU one, that would almost be easier to show just because like it makes sense with a square. If you're gonna square something, it's
Yeah.
like multiplying it once, or you're multiplying it twice, but if you just don't do it afterwards, it's multiplying it once.
That's right. That's right. That's right. Okay, now the last question on her review here is a really good one that I am testing you on. So let's read it. Okay, it says compute the standard matrix for the linear map that takes vectors in the form x, y, z and spits them out into R2, x plus 5y plus 5z, and then 2z. Do you follow how what I did for you there is I translated his notation. I think it's a man, yes, Stefan. I translated his notation to our notation. The input vector x, y, z exists in R3. The output vector exists in R2. Okay, so what matrix does this? Okay, it's really simple. The matrix that does this is 1, 5, 5, 0, 0, 2. Okay, if you want to see kind of where that comes from, we can think of it like this. Think of it as, this could be written as x times 1, 0 plus y times 5, 0 plus z times 5, 2. Now, isn't that neat how it's really showing matrix multiplication? It's showing, oh, then this must be the first column of the matrix, and that must be the second column, and that must be the third column, if those scalar weights go on them to make this. Okay, so ready for the on-to and one-to-one?
Is that just the answer?
This is the matrix. What was the question? The question was, compute the standard matrix of the linear map. We have it right there.
Did we
It's a matrix that does it.
didn't we do something about like breaking dimensions up and down? Like,
Yeah.
wasn't there like some violation? We weren't allowed to go one direction.
Well, I think what you're thinking of is the fact that, no, you can go either way, right? But I think what you're thinking of is when things are not invertible, then, right, you can't go back. For example, if you project something onto a line, you can't go back and find the vector that it came from.
Got it.
Yeah. Okay. All right. So is this onto? Do these vectors span all of R2?
Yes.
Definitely. This is onto. We'd say it's onto R2 because we have a pivot in every row. Good job. It's onto R2 because we have a pivot in every row. Those vectors will span all of R2. Now, it is not one-to-one because we can't have a pivot in every column. This means that pick a vector in R2, there will be many ways to get to that vector, not just one way. Remember, being one-to-one means that for every output, there's exactly one input. Whereas just being a function is that for every input, there's exactly one output. Okay, it's 3:03. That was a lot. I kind of want to keep going just because it's our last chance, but
Can you
What's
tell us,
the-
can you
12
review
more
something that
minutes
you
for-
really think will help us?
review something that will really help you on the test. I mean, honestly, it's quite a coincidence, maybe not because it's the same course. But this was a really fantastic review. I didn't make this myself, but it was very, very good.
Like, oh, we just.
Like, I mean, this page, this page of 10 problems is excellent. Okay, I mean, especially since because I got excited about it, I wrote a question like number 4 on the end. Okay, but yeah, let's find 1 or 2 more things for you to try, and then we'll call it a day.
You know, like a transfer or generation on the line, or like
rotate our quarter or something like that?
Oh, sure. Like where we do something that's not going through the origin sort of thing? Sure.
Correct and left decimal line.
All right, so let's make it up from scratch. Let's say rotate the quadrilateral formed by -1, 0, 0, 6. Trying to map this out in my head as I do this. 0, 6, 4, 1, and 3, -3. Rotate the quadrilateral formed by those vertices about the point -4, 4. Yeah, that'll keep you busy for a while. Try that. Okay, pause the screen, pause the record.
Do you have the ones under?
All right.
I might have split my book. Let me-
There's the revealing. Okay, so let's describe what happens. Okay. This matrix on the far right contains the homogeneous coordinates
So do you always have to-
of the quad. Yeah, I can raise it up. All right, there we go. That contains the homogeneous coordinates of the quad. It's always on the far right, right? These are the things that we are transforming. Why are the ones there? Because it's homogeneous, right? We're lifting it off the plane by 1. Okay. This thing moves the center of rotation to the origin. So it moves the center of rotation to the origin. Okay, this thing rotates and this thing moves back. And of course, yep, these are matrices, so order is very important. So of course you can think of them being done in any order you want. You can think of these two happening first, and then this one, and then this one, but the order in which they're placed is important.
I didn't get -2.
No? There's something wrong with one of your matrices. There's so many entries to make a mistake here.
Hold on.
What? Is this 39 entries that you have to type in?
No, I should have this right. I think I just missed a negative and I was typing.
All right,
That's a fourth cycle, we only would be like the.
What's that?
Yeah.
I told you it would be a triangle.
Yes, there is.
Have we always put the A?
There, I just gave you another question, because now that we've done this, that's basically. It's a little, there's some modifications that make it a smidge different, but
I keep getting -4.2, but my matrix actually. You know, it's just-
oh, could you be in radians?
No, in degrees, missing a negative.
Yeah, you're missing
That is negative.
Yeah.
So the first 3 equations are just like the transforming part. and you
Maybe
always
I'm
have to
thinking
put
my
the
yes.
my original logic.
We actually want
that one.
do something,
Yeah, you want this,
right? We don't want to just
Yeah.
transform nothing, you know?
Yeah, no,
That's
it's-
kind of random.
Is it diagonalizable? I mean, there's just one next to you, right? That's key first. Yeah, that's what I'm saying. Find the diagonal would be right in the key. Okay.
And D
Ah!
contains eigenvalues.
Yeah, these eigenvalues, eigenvectors. Eigenvectors.
And the algebraic multiplicity is how many times you write it?
And the geometric is the dimension of the eigenspace. Right? Okay. Oh my goodness. It's exciting. No, I'll take it. All right, so exam next class. That's all we'll do next class. If I don't have a chance to tell you, be safe and make good decisions with your strong weekend. Don't want anybody to looking at you. Ooh, that would be a fun question to answer. We all graduate. Who do I think is the most likely to do that?
Definitely not like that.
What is that?
Well, you have decisions that a responsible adult would not make.
Those things are run.
I'm going.
Most likely to know. Yeah, I think that's a good. That'd be fun.
I wouldn't
You
say-
already answered.
Stay hard. Bye. Have a nice night. See you Thursday. Bye, everybody. Wow, I actually.